Hello guys, welcome to my talk on reproducibility in machine learning from theory to practice. I'm Koustuv Sinha. I'm a PhD student at McGill University and Mila, and I'm also a research intern at Facebook AI Research. And I'm excited to present to you this talk on reproducibility. So we will be covering various agendas today. So first of all, we will be looking at why do we need reproducibility in science? Then we will be looking at a few case studies on the need of reproducibility in machine learning. And then we will talk about what is the machine learning community doing about it. And then finally, the most important part, we will cover how can you perform reproducible research. Now, reproducibility has various meanings in science. Most of the cases, reproducibility refers to the ability of a researcher to duplicate the results of a prior study. Whereas there is another term like replicability and reusability, which are also used in case of reproducibility. So basically, we want our experiments to be replicable and reproducible by people who are trying to use our methods, our code, such that our experiments are solid and robust. Now, there exist a lot of differences in terminology. So just for the sake of presenting the terminology of the talk, I give you this this table where I say that if you have the same code and analysis, and if you have the same data, then we call it a reproducible work. A replicable work considers different data, presumably sampled from a similar distribution or method. A robust work assumes that the same data but different analysis, such as, let's say, reimplementation of code, perhaps different computer architecture. And then finally, generalizable work leads to the same conclusions despite different data and different analytical tools. So is there a reproducibility crisis in science? Well, it turns out yes. In 2016, there was a report published in Nature called what is the reproducibility issues in science, and majority of the people, 52% of the people said that yes, there exists a significant crisis. And when asked about what are the different domains where people say that there is a crisis, chemistry, biology, physics, and medicine come up in the top 4 criteria. Now, computer science isn't shown here, but definitely computer science is within the top 10 domains where we have a reproducibility crisis, even though we shouldn't be having, because it's the same code, so it should be working in the same way, right? So what are the findings that we have in terms of computer science? And so in computer science, we can think about that, okay, reproducibility should be easy, right? I mean, you have the same code, you have the same amount of data. And if I give this almost the same amount of computation, I should be able to get similar results, right? Well, turns out it's not. So in Europe's 2019, there was a nice paper known as A Step Towards Quantifying Independently Reproducible Machine Learning Research. Now, in this paper, the author found out that 63.5% of the papers were reproducible, but the rest were not. And significant factors which affected reproducibility include the absence of pseudocode, the absence of proper hyperparameter, poor readability of equations and tables, absence of specific details of what is the compute needed, and also the primary topic, such as which subdomain it is, affected the reproducibility. Now, the author did report that 85% of the results were successfully reproduced after the assistance from the original authors. So that is a very important task, whereas compared to 4% when the authors didn't respond. So communication with the authors is a very critical tool in reproducibility. Now, this study has a major limitation that it's only one person who have been doing this reproducibility effort over the span of 5 years. So I should take this paper with a grain of salt, although it paints a very grim picture of what is happening in the community right now. So let me go through a few subfields. So one of the major subfields and probably very important subfield in case of medical imaging is computer vision, where you're given an image and the computer sees some format of that image and then predicts, let's say in an image classification task. So usually you take like a deep model, like such as ResNet or DenseNet in terms of like X-ray architectures, and then you try to like predict what is the pathology of the X-ray, for example. But is this field also prone to reproducibility issues? Well, turns out they are. So there's a nice paper known as Unreproducible Research is Reproducible. So in this paper, they experiment on 10 different seeds, and they show that different models vary differently with like different seeds. And that is very concerning. And this single initialization of the seed is a brittle thing. So you need to like present your reports across a number of seeds. And it is more true if you have like a much simpler data set, for example, MNIST, or it's also much true for a smaller data set. So in medical imaging, we usually work with chest X-rays, and we don't have like too many data like to work with. So these like this brittleness of the seed issues also come up like really like it's also like a very big issue in terms of medical imaging. So we need to be careful about that. So in this paper, essentially the author did a very nice work on comparing different architectures, and more or less the author found out that certain architectures are more prone to the brittleness of the seed. Okay, so let me go to another subfield. So this is a field known as generative adversarial networks, which most of you already know about. And so here, basically, you have a generator and a discriminator, where the task of the discriminator to decide whether the image is being generated by a computer or not, whereas the generator, its task is to fool the discriminator. And there has been an explosion of papers on this topic over the last 5 years, and we have seen rapid progress in the field of computer generation. Now, are GANs also susceptible to reproducibility issues? Turns out yes. So there's this paper called Are GANs Created Equal? A large-scale study. So this paper looks at a wide range of hyperparameter search. So basically 100 hyperparameter samples per model. And then they show that no model is significantly more stable than the other. So essentially the models are very much unstable to the little bit of fluctuations that you have in the hyperparameter. And when you report your results, if you have a limited computation budget, which we all have, you would not be able to search through all possible hyperparameters. So you would possibly miss like the best hyperparameters. And this paper did like a very thorough study of different hyperparameters and found out that even the baseline models can be made better by a little bit thorough hyperparameter search. So basically discussing the best score obtained by a model on the dataset is not a meaningful way to discern between these models. One should instead discuss the distribution of the obtained scores. Now, let me go into another subfield known as reinforcement learning. So reinforcement learning, as we all know, it's a very exciting subfield where it's a dynamic model which is interacting with the environment, where there is a state and a reward that like the agent gets when it plays out an action. And this is a very general framework for sequential decision making. And this has been used and also being used in very many wide applications, starting from robotics to financial trading and so on. Now, reinforcement learning in particular is very susceptible to reproducibility issues. So the paper Deep Reinforcement Learning That Matters like pointed out this issue in a very great detail. The paper basically found out that in reinforcement learning, proper reporting of hyperparameters is very much required, as well as the difference of seed. But most shockingly, difference in implementation also gives you different results. So the paper looks at like a very popular model known as TRPO and looks at many public implementations of TRPO and finds that there are significant differences in the convergence of the different like implementations of the same algorithm. So different results, like different code-based results in different hyperparameter choices. And then the paper goes into like more detail into what are the different significant effects. This basically like brings up the need of reproducibility in this hour. Now, if we look at like this paper in a little bit closer, what they also found out that if you even have the same algorithm, same code, same hyperparameters, but you just vary the seeds, your results like fluctuate rapidly even after doing random averaging. So the number of seeds plays like a critical role in reproducibility. even the number of trials per experiment is not standardized. So what basically papers report different number of trials. So that is like number of trials you do on the number of seeds. So since that is not standardized, how can you take the result of a paper in its value, right? So you have to be very careful in these regards. So basically, if you don't take enough samples, then you can easily beat your baseline. Whereas if you take enough samples, then your mean will be somewhat lower than the baseline, or maybe like close to the baseline. So there are less incentive for people to show many iterations of the same experiment. But if you are honest about your research, you should be caring about this. So basically, from fair comparisons to robust conclusions, we see that different methods have distinct set of hyperparameter set, different methods exhibit variable sensitivity to hyperparameters, and what is the best method often depends on the data and compute budget. So what are we doing about it? Like as a community, what are we doing to tackle this reproducibility issue? So I would first talk about the open science movement. So this is not specific to computer science. This is a very general movement, but computer science is very rapidly taking a good part in it. So basically, I will talk about few of these things, such as taking reproducibility as very seriously. So basically, we have a journal known as ReScience, where we submit the reproducibility reports. And then we also have checklists coming up, which suggest how to do better experimentation and better code design. And more conferences are making code submission mandatory. And with it, conferences are having code submission policies. And as well as I will talk about reproducibility challenges, which are a very nice and exciting domain for people to try out the reproducibility of different papers. So the ReScience Journal is essentially a platform to publish reproducibility reports. It has an extensive review process because it's a journal, and you can submit your reproducibility report along with in this journal, and also the reproducibility challenge publishes its reports in this journal. So this is why this is important, because being a journal, it makes reproducibility a nice citable venue. So basically, whenever you are doing a reproducibility report, it's not just any other report, it's also a paper on its own. So, and to give merit or to give a little bit or a lot of credit to these papers, we can publish this in the ReScience Journal. Now, the ReScience Journal is basically meant for open reviewing. It's on GitHub, and it accepts reproducibility reports on a vast array of fields. So maybe in this MICCAI Hackathon, you will be able to work on some reproducibility reports on several MICCAI papers, and you can also end up submitting those reports in ReScience, where you will get a citable publication once it's accepted. And it has a large team of editors for rolling reviews over the year. Next, I want to talk about the reproducibility checklist. So the first machine learning reproducibility checklist was introduced by Joël Pineau in 2018. This is a minimal information that must be included in the manuscript. So this is not necessarily exhaustive, but it's basically a set of guidelines for the authors to look at. And these guidelines look into what are the what are the different models and algorithms that are presented in this report. Then if there is any theoretical claim present, then whether there is a clear statement of that claim. If there are data sets used, then what are the relevant statistics of the data sets are used. If there are code shared, then what are the specifics of the code are shared. And if it's an experimental results, then whether range of hyperparameters are considered, proper error bars, statistics are given. And these are essentially very detailed checklists, but still it's not super exhaustive. And this is just meant to be a checklist that you look at while you are submitting a paper. So this will help you to submit a better version and a better reproducible version of your papers. And during NeurIPS 2019, authors were obliged to fill in during both initial submission and final camera-ready submission. So since authors filled out this submissions, we could collect the statistics, and we basically analyzed what the authors did during initial submission and camera-ready submission. So we have some interesting results that basically authors, for example, 36% of the papers judge the error bars are applicable to their results, while 87% see clear value in defining the metrics and the statistics used. So it's kind of like a weird result, because if majority sees there are clear value, then why not that same majority see that judging error bars are applicable? So we saw that a lot of the cases or the lot of these answers changed while the paper changed from initial submission to camera ready submission. For example, link to the data, link to the code, and basically these things like changed because people tend to like submit code after the at the camera ready deadline, and that is also like very much acceptable. So we also introduced like code submission policies, and you see the transition diagram here on your right. So this transition diagram shows that how many papers had code available during initial submission to final camera ready. And we saw that there is a major increase in the number of code being available. And that is also very encouraging. So 40% of the authors reported that they have provided code in the initial submission, whereas 71.5% of those submissions were confirmed by at least one reviewer. And availability of code at submission was positively associated with the reviewer confidence. So having code is good. Now, let me talk about the machine learning reproducibility checklist. And so basically, does the checklist affect the acceptance rates? As of now, no. And do reviewers find the checklist useful? And that's a resounding yes. So basically, a lot of people reported that the checklists were easy to use. But for now, we are like the reviewers are not being told to be basically incentivized for the checklist. So essentially, it's just like a soft checklist to be in place. It's not like a super mandatory thing. But still, it's very useful. And I would encourage you to read our report on the paper and the checklist, which were used in NeurIPS 2019 reproducibility program. Now, there's another checklist, which is known as the Machine Learning Code Completeness Checklist. And this is introduced by Robert Stojnik from Papers with Code in 2020. And this enforces like a good guideline for open source code released by the papers. And these guidelines contain like dependencies, training scripts, evaluation scripts, pre-trained models, as well as the results. So you should like try to give all of these things in your README file such that people find these information and then they can reproduce your work. And what they saw that NeurIPS 2019 repositories with more than 5 ticks of basically with all of these criteria matched, they got a median of 196.5 GitHub stars than the median of 1.5 GitHub stars with none of these criteria matched. So that is a very strong signal that having your research to be well communicated is very important. And then finally, I'm going to talk about the reproducibility challenges. So these are basically challenges which you can participate and you can help the community to better understand the reproducibility of existing work. So, so basically the machine learning reproducibility challenge was used in like the inaugural edition was at ICLR 2018. And then till date, we have 3 editions. And now we are running the 4th edition of ML Reproducibility Challenge 2020. So in terms of like we started from NeurIPS 2019, we chose the only papers from the accepted list, whereas before we chose from the submitted list. But now we are only working on the accepted list because the paper qualities are much better to work on. And the general format of the conference or the reproducibility challenge is that you, after a conference is done, you can claim papers of the conference and then you can submit papers on different tracks. So baseline, ablation, or replication study. And then you can submit them to open review where we do open peer review for all of these reproducibility reports. Actually, we took the same reviewers from NeurIPS and ICLR, and then we have a journal publication to ReScience C. So the Machine Learning Reproducibility Challenge in NeurIPS 2019 saw a large number of participation. We saw 63 universities, 10 institutions, and 5 machine learning courses directly signed up for this reproducibility challenge. And we hope that given in the coming years, we will see more and more participation across the broader range of different courses, because this reproducibility challenge serves as a very nice introduction or a very nice like final project for different courses, machine learning courses. So basically the related work in the community, there are also EMNLP reproducibility challenge, which is run by Jesse Dodge et al. With University of Washington. And there are several workshops in ICML and ICLR where people talk about reproducibility. So these basically cover the steps that we have taken in terms of reproducibility in machine learning. Okay, so in the second part of the talk, I will talk about how can you perform reproducible research. So let us start with a simple example. Say you have an awesome research idea like transfer learning on MNIST dataset. So in transfer learning, you have like 10 different tasks and you're learning from one task and you're transferring the information to other tasks and you're trying to see how much forward or backward transfer you can leverage. So this can be any like research topic. I've just taken this as an example. So when you start your research, you set up the basics such as training and test pipelines. So you set up with the data loaders, you set up with the training loop, the test loop, and then you run the experiment, right? But then when you start to like go deeper into your research, you find out that you have like too many arguments to keep track of. Now you can, although you can keep the arguments in like in Python argparse, but still like if you want to like change a lot of arguments every time you have to change in a command line, or every time you have to like save a default value in your code in the argparse. So a bit better method to use basically like config files, and that is the first practice. So basically config files make it easy for you to manage different configurations for different hyperparameters. You can either use a JSON or YAML config file. Personally, I prefer YAML because you can add like better comments. And then running the code is simple because you can just run the code with giving the name of the config file. So if you run like a large scale hyperparameter searches, you can even generate config files for each of the parameters sweep, and that helps a lot in maintaining like sanity in your experimentation. So you can also like check out Hydra. It's a like a relatively recent but very cool and stable platform, which helps you to give different configuration files, as well as it helps you to maintain different inheritance in configuration files. So now that you have set up the experiment, you have a good configuration set up. Now you're doing inference of your model. So ideally, you first infer on the validation set, and you can also write a separate inference script to evaluate on the held out test set, which you do at the very end before adding it to the paper. But for this script, you obviously need to save your model. So the second practice is effective checkpointing. So the ideal guide for checkpointing is save as much as your resources permit, but ideally it's still okay to save the last epoch and the best performing epoch. So whenever you have your code, you take into account like, okay, this is the best performing epoch for my given validation metrics, and then you save your model based on that validation metrics as well as the recent epoch. And if your model is long running, then consider saving within your epoch such that if your model crash for some reason, then you can recover from the same checkpoint. Now, basically the way I like to save my checkpoints by giving like an epoch number. And if you use something like PyTorch Lightning, so which is a really nice platform, which I will be talking about. So PyTorch Lightning gives you a really great practice for saving these checkpoints. And you can also save the checkpoint with your validation metric score. Now, once you have like your inference ready, now you see that your model is not giving you good scores. So you need to inspect like how the model is performing. So how do you do that? So the first thing that we do while inspecting is that we look at the training loss. And the best way to look at the training loss is that you have to perform extensive logging of your different training metrics as well as validation metrics. So ideally, you can save the logs in a log file. you can use Python logging module to save it in different, in basically a log file and then generate plots. But these days you don't have to like go into all of that because you have access to really nice platforms such as TensorBoard. So TensorBoard helps you to give like nice interactive visualizations of different training runs and validation runs. And the key cool part about TensorBoard is that you can run it locally. So you do not have to host it anywhere. You can just run it on your own server or your own laptop. Now, there are other logging services which are coming up, which is becoming very popular. One of them I'm porting out is Weights and Biases. So it's a really nice platform, but it's a hosted platform. So just make sure before using it is that if you are in industry, then whether your company has the necessary rights to upload your data to a third party. Otherwise, if you are an academic, then it's a pretty good thing to use because they give free accounts to like academic emails. And your logging, like your different logs that you upload there, they are very well polished logs, and you can do extensive search. You can search through your hyperparameters. You can play with your different like plots, and you can interactively look at different things that affect your model. Now, there are many other like libraries out there, for example, CometML, Wisdom, MLflow. So I'm not talking about a lot of these in this talk. I'm just like merely pointing these out to you. So TensorBoard, still people prefer it because it's local. And these days there's also TensorBoard like online version available where you can upload your logs and share it with your collaborators. So basically practices 1 to 3 talk about effective experiment management. And now setting up the boilerplates for 1 to 3 are an useful practice. Like if you are like a PhD student, I would encourage you to set everything up from scratch with your own code, because that will help you to understand what exactly is going on. But let's say if you are in industry, or if you are like a senior PhD, and if you don't want to like repeat your old mistakes, you can take help of like these different libraries. The one library that I really like is PyTorch Lightning. So if you are working on PyTorch, then it gives you a really nice wrapper to maintain your training, testing, and validation flow. And then it also helps you like logging, experiment management, checkpointing, all the good best practices. But it's still like a different framework to build your models. And it's a very flexible framework. And you can also look into like Sacred and MLflow. So these are also like different frameworks that you can use in your work. These days, I just use PyTorch Lightning because for my research flow, it suits the best, but it totally depends on your research flow. And as I said, if you're an early PhD student, it doesn't hurt to like build the entire platform by yourself. Now, all is good, but something is still odd, that you're running multiple runs of the same experiment, but you're getting different results. So as we talked about previously, you might have forgot to set the seed. Now, basically what you need to do, before running the experiment, you need to set aside a seed, and you should not optimize on that seed. So I have given you a snippet, and this snippet basically like gives you different seeds that you can set. So you should set the random seed, the NumPy seed, and the PyTorch or TensorFlow seeds. But it's crucial that you do not optimize on this seed, because this is a very it's very tempting to do that. I understand, but you should not. So the best process would be, let's say you take any n number of seeds, you set that aside, you work on one seed, and when you're ready to report your result, you report an average on those 10 seeds which you have set aside, and that will be like perfect for reproducibility. Now, you also need to keep an eye out for GPU reproducibility, because it's not guaranteed, and you should check out the documentation for PyTorch and also for CUDNN, what they say about reproducibility in GPU, because unfortunately it's still not like fully reproducible. I mean, you can still go into that length if you want. It will like slow down your training, but at least like maintaining like a healthy level of reproducibility using these seeds are very beneficial in your experiments. So, okay, now you are deep in your research, but you forgot what exactly or which line of code you changed last night while being caffeinated. And it happens a lot with me. and now you're unable to reproduce your own results. Well, facepalm moment, right? So what did I do to make this work? And to get that answer, the next practice is versioning your code. And this is a no-brainer. You should use like a version control system such as Git from the very early in your code base. And you should commit early and you should commit often. Like whenever you are adding a new functionality, whenever you're fixing a new bug, whenever you're running a new experiment, you should commit. And that will give you basically nice reproducible results within your own repository. And you can also add the raw result of your experiment in the commit message so that you remember what point you left your work. So let's say you got like, let's say 90% at this point and you add that as a commit message. So that will also be like really helpful for your future self. Now, GitHub is your friend, so you can upload your repository in GitHub, and these days GitHub offer you unlimited private repositories, and then you can take use of that, and you can tag version of your project to separate on major decisions, and you can also have separate branches for small proof of concepts. So you can also use GitHub issues, for example, to track your project, and it's essentially a really nice tracking and platform. So now, another main thing that we tend to forget while doing reproducibility is minding your data. So let's say in the transfer learning setup that we talked about, you decided it would be a good idea to mix certain classes of fashion MNIST and MNIST digits, but then you went a bit too deep down in the rabbit hole. And then you ended up with different configurations of the data set that you're working on. And then you end up forgetting, okay, which configuration gave me the best results. So you also need to be mindful of your data, and that is our next practice. So track your data. It's the easiest way to track your data is to add it to the Git version system directly. So let's say if you're working on small text files or like CSV files, you can directly upload that in GitHub. But we tend to work on a much larger data set, especially in medical imaging. You're working on large chest x-rays, so it's probably not useful to push the entire data in GitHub. So there are other things that you can try. So one easy thing to try that you can compute an MD5 hash of your data directory and save the hash in your config file. So whenever you're running your experiment, you compute the hash and then you compare the hash in your config. And then that would give you like a good sanity of if you had changed anything in your data. Also, you can back up like your data periodically using Google Drive and AWS S3 buckets. You can also make use of data version control. Like that's a nice library to track your data. And basically you should like back up everything such that whenever you're reproducing that result, you should get the same data that you ran in the first time. Now, let's say you're building a data set for the public, you should also be considerate of adding like data sheets. So you should look at this paper, data sheets for data sets. And this paper motivates that you should have a README for your data set, which contains motivation, composition of the data set, collection process, any pre-processing steps that have been done in your data set, what are the use cases, what are the distribution, and how will you maintain the data set in future. So these are the things that you should add if you are releasing your own data set. Okay, so now you have results and it's time to make some shiny plots and analysis. So let's say you have nice results and you want to discuss with your supervisor. You find a cool plotting function online and you generate shiny plots. The supervisor always asks you to modify the plot to his and her liking, and you can't seem to find your plotting script nor your output file. So these are like real plots taken from like really nice papers. I would suggest you to look at these papers if you really like the way they plotted. These papers themselves are quite cool too. So while plotting, what you do, you like basically maintain a set of Jupyter notebooks. And this is our next practice. So Jupyter notebooks give you a nice reproducible way to do good data analysis on your experiments. You can do result analysis, you can do plot generation. You can also do table generation in your notebooks. And these notebooks can be used to share intermediate results with your supervisor, with your collaborators, and you can use GitHub to render the notebooks in your discussions. So you can share a GitHub link to your notebook, and that's it. People can see your notebook in the browser. You can also use Jupyter Contrib extensions to supercharge your notebooks. That gives you a nice list of extensions, such as like foldability, tracking, and etc. You can also use like Jupyter Lab. So that is like the next version of Jupyter, which gives you a lot of these nice functionalities. And while like reporting tables, you can use pandas, and you can use the pandas to LaTeX to directly write your results in a LaTeX table, removing error-prone copying of results into LaTeX. So our next practice is coming up with that is reporting results with error bars. So as I've given you the motivation, like giving results with like error bars is very important. It gives you the whole distribution of what your proposed method covers. So once your pipeline is run, you should run your experiments with multiple seeds and report on the variance of the results. And even if your variance is pretty big, it's still fine to report that. Like reviewers will not be like super critical about it, hopefully, because like the variance is a very, very useful figure for reproducibility, and you should be upfront about it. And you should add this seed, like all the seeds in your config file when you release your reproducible code, such that people can use those seeds and get the same variation. And you should also like choose arbitrary seeds, of course. You should not like run any grid search on it. And you should also basically add confidence intervals in your table. So let's say you're presenting a table, you should also add like plus minus confidence interval. So basically statistical testing, and highlight statistically significant values. So that would also help in reporting your results. And you can report your results on multiple seeds, but another higher bar of like reproducibility is to report on multiple data sets or multiple data set splits. And then you can have like a confidence interval or variance over multiple data sets. And that would also be like pretty cool to have in your paper. So now let's talk about dependency management. So irreproducibility often stems from software deprecation. So basically, to replicate a published work, the first thing to do is to match the same development environment containing the same libraries that the program expects. Thus, it is crucial to document the libraries and the versions that you use in your experiments. So basically, after your experiments are stable, you can leverage pip or conda to collect all libraries that you have used, such as like pip freeze to requirements.txt or equivalent in conda. Or you can use like poetry. So this is like a new upcoming version. And basically you can like write these requirement.txt or environment.yml in your repository. And that would give like anybody who are reproducing your work the exact list of libraries to work with. Now, for better reproducibility, you can consider using Docker or Singularity containers. So Docker is essentially a headless virtual machine that basically you can upload to Docker Hub, and that contains the exact same configuration that you use to run your code. And you can use that, and you can basically like release your Docker Hub or your Singularity containers. Singularity is useful because you can run it in HPCs or high performance computing clusters. And you can also use something like repo to Docker to convert your already existing GitHub repository into a Docker file. So now the next practice, which is also quite obvious one, is open sourcing your research. So after your paper is released, consider open sourcing your work. This adds visibility to your paper, and it encourages people to like look into your paper, look into your code, and it encourages you to produce like reproducible research. And you can also submit your like code base to Papers with Code. It's like a really nice platform where you can share the code base, and then people can look from that platform and find your code and like add stars if they find it useful. So while open sourcing your research, you should also have like a pre-release checklist. So basically there are some guidelines is that you should squash all the commits in the public branch. So why this is useful? Because when you're doing your research, you might have a lot of silly commits, you might have a lot of silly bug fixes, you might have even some API information released in certain commits. So you want to like nullify all of that. So you should squash your commits to a single commit. And then you should also make sure your code doesn't contain any API keys or logging keys, such as if you're using weights and biases or CommentML, you should be extra careful of not leaving those keys in your code. So now once you squash your commits, you end up with a single commit, but once it's released in the open, then people can work on it and then people can add more commits to it. And then you can track using the nice commit functionality. So you should also keep an eye out for hard-coded file locations. So that comes up a lot in my code and I have to like manually remove them. And you should also format your code to improve readability. So if you are using, like, let's say in Python, you can use like black. It's a really nice formatter, which will format your code in a very readable way. And you should also try to document your code. Now, this is a, like, we don't usually document our code that much in machine learning, but we should really be doing that because that helps not only people reading your code, but also yourself if you want to come back to your project, let's say X months down the line. Cool. So now our next practice is effective communication with README. So this practice essentially follows the ML code completeness checklist, is that whenever you release your code base in open source, you should make sure that your README contains like the information about the dependencies, that is like what are the libraries are used. It should have like scripts which call your training function with the same hyperparameters. It should call your evaluation scripts. It should also have link to pre-trained models. So if you are working on some like public domain large scale models, you can also like upload your models to any public space. Let's say you can upload your model to a Google Drive and then you can share the Google Drive links in your README. And also it's quite important if you share your results in a table such that whenever somebody is reading your code, they can just directly see, okay, these are the results, and then they can compare and against your code. So as I've shown you before, like the papers with code people, they found out that repositories having all 5 of these criteria, they tend to have like a median of 200 GitHub stars, which is quite cool. So it's also good to have basically a contributing guide, and a blog post. And a blog posts are coming up like really, like it's very ubiquitous these days, and it's very good to have like this accompanying blog post for your paper, such that people can read and understand, okay, what is exactly going on. Cool. So now we are almost done. This is our final practice. And this final practice is test and validation. So additionally, you should test your setup on a separate machine to ensure that you have a reproducible build. You can use Google Compute Cloud, AWS, or Azure to spawn up a small environment, and then you can test your code, like just the inference of your code, because that will help you to remove like hard-coded paths if it exists, and it'll also make sure that your dependencies are okay. You can also check out CodeOcean, which is like a nice platform which provides isolated AWS instances tied to Jupyter notebooks for easy evaluation. And you can release the CodeOcean platform, like you can share your workflow to the users. That would give you like a really nice way of reproducibility. So nice. So we have covered our talk. So basically the key takeaways are reproducibility in machine learning is extremely important for the advancement of the field. The machine learning community is coming up with innovative ways to encourage reproducibility in the form of reproducibility challenges, journals, checklists, and so on. And you should commit to reproducible research early on in your workflow. And I hope that the practices that I showed will be useful for your own work. And I have also released these practices in a form of a blog post that you can find in my website. I will also add this link in the forum so that after this talk, you can go ahead and check that out for yourself. And then finally, I want to conclude with a statement from my supervisor, Joel Pinu, is science is not a competitive sport. So we should be like basically approaching science with the same amount of care. And basically you should be you should be taking time out in doing your research. It's not that you have to beat someone. You can take your own sweet time. You can focus on what are the important stuff, and you can make sure that your code and your work are reproducible. So finally, I'm proud to let you know that we are running the Machine Learning Reproducibility Challenge edition. We have partnered with Papers with Code. And the cool thing about this edition is that we are covering papers submitted to NeurIPS, ICML, ICLR, ACL, EMNLP, CVPR, and ECCP. So there are 7 conferences that we are covering. So there are a lot of papers that will be available to you to work on reproducibility challenge. And then you can submit the challenges, and then we will have peer review. And then the papers will be published in ReScience Journal, as well as the papers will be made visible on Papers with Code. And this will be a nice opportunity for you guys to work on and contribute to the reproducibility of papers. So basically adding extra information to the papers that are already available in order to make them much more stronger. So thanks for listening. If you have questions, feel free to hang out in the forum, and then please ask me questions. I will be able to answer them. Special thanks to my supervisor, Joel Pinu, for her constant encouragement and support, and Shagun Sudhani, Jessica Ford, Matthew Muckley, and Michelle Pagnini from Facebook AI Research for giving me very, very great insights and tips for writing this talk up. And these are all the different people that I want to thank, from Reproducibility Challenge to Open Review to NeurIPS Reproducibility Program, and especially the ReScience people for promoting reproducible science in machine learning. Thank you, and thank you for listening to this talk.